Sure. Alrighty, welcome back to 454. So yeah, the course pretty much done. So we'll be doing some quick final review of everything that you need for the final. And then past that, we can do fun stuff at the end whatever we want. But yeah, Monday, always a bit late. So let's get into how your final will work. So it will cover all the material from the course. It is on the 19th, so remember it's quite a fair bit away. Remember, since I canceled Friday's lecture, I'll do a review session closer to that date when you actually pay attention to the stuff. But this is mostly so you have the recording, you actually know what to expect on the final and everything like that. So it will be cumulative. There'll be CPU architecture, compiler optimizations, performance optimizations, not to the same degree as your midterm, since that was all your midterm. Then stuff we did after, cache performance, a little bit of dynamic memory and modern allocators. Then we moved on to thread synchronization, which was mostly review. Parallel architectures, performance, better locking methods, and avoiding locking through using the atomics themselves. Then we got into a bit of MapReduced, and everything will be done, like the final content will be based on the lecture and the labs, probably less so the labs. So let's go through it quickly. So what did we learn? So started off sequential program optimization, talked about CPU architecture, profiling, which was optional from lab 1 on. Hopefully you used it. I guess some of you did not. Some compiler optimization, the memory hierarchy, cache optimization, talked about coherency and consistency, dynamic memory, then threads, synchronization, parallel architectures performance, and again, locking and avoiding locking. So, review from the beginning of the course. Start off brief review, or brief introduction to some of you, CPU architecture, so some things that make a CPU fast, pipelining, filling up every stage in our CPU all at one time. We had branch prediction, and then to make things fast, real CPUs do out-of-order execution. We might have some instruction level parallelism where a single instruction issues multiple operations at the same time, and then some simultaneous multi-threading, or SMT. So if we focus on Intel, this is basically how it looked like through history. So 71, no pipelining. You just had how many cycles the instruction took is the cycles per instruction. Then once we added pipelining and branch predictions, we got closer to 1. And with branch predictions, we got even closer to 1. So just 1 cycle per instruction. After that, we tried to do things in parallelism. So 1 is the best we can get without any parallelism. Moved on to superscalar. That was just having like multiple add units on our CPU that can all run in parallel, or multiply units. GPUs and tensor units, and of course, take that to the nth degree. But that's the idea on a CPU. Then we had out-of-order execution to keep that pipeline filled up. And then simultaneous multi-threading, which just essentially stole instructions from multiple threads in order to keep that pipeline all filled up. So did some profiling, used gprof, gcov, which isn't really profiling, it's just a coverage tool to make sure that some lines are executing. Unix time command, which was just wall clock, which is currently what your users see and what's being evaluated on lab 5. And then perf to get a whole bunch of other details about what's going on. You can see cache misses and actually hardware events from your CPU. So the rationale behind profiling before you start optimizing things: premature optimization, root of all evil. And we, of course, had Amdahl's law, which basically gave us a cap on our speed up. So our speed up was old time divided by new time. And our speed up is kind of limited by Amdahl's law. If we can only speed up 50% of our code, even if we make it take 0 time, well, our overall speed up is still only 2 times. So that would be our implication of that law. All right, then we got into compiler optimizations. We found out that some compilers are better than others at certain things. So most CPUs, like if you do GCC or Clang and you use O1, you get simple things like constant propagation, folding, sub-expression elimination, copy propagation, dead code elimination, loop invariant code motion, just moving stuff, and function inlining. So it will only inline stuff that it knows is profitable, so really, really small functions like getters or setters or something like that, if you're doing it in C++ land. And then, well, we had O2 and O3 that might do slightly different things. It will try and do some smarter instruction scheduling, maybe do some loop unrolling that you might have to do manually, might try to do some vectorization. Well, it should try and do vectorization. As we saw, Clang was a lot better at this than GCC. GCC was kind of bad at it. And then found out that, hey, we should probably just look at our outputs, make sure that our compilers are doing the right thing. Otherwise, we might need to help them, especially with loop unrolling on some CPUs. So your role as a programmer. So we don't want to prematurely optimization. We don't want to smash it into oblivion. Make everything hard to read, just make everything a giant array and pointers everywhere. You want it to be easy to read and only optimize it if you absolutely have to. So some things to do before you start smashing it to bits. Select a good algorithm first, because without that you can't do very much. Write some code that's readable and that someone else can read and hopefully maintain. Write functions, maybe use recursion, although some of you still don't like recursion, maybe. So, or you can use other functional stuff or different languages that hopefully prevent you from doing silly things. Might have to eliminate some optimization blockers. Again, you're kind of helping the compiler do its job. The easiest thing to do that we showed was very successful is enabling link time optimization. Probably should do that, unless you have a reason not to do that. It can slow down your compile times if you have a gigantic program, but for the most part, you're good to just leave that as the same default. And of course, if we have really, really, really looped codes, you want to focus on the inner loops. Those are the hotspots in the code. Do your optimizations there because, well, that's going to be executed the most number of times, and that's where you should start your focus. So then we got into cache performance. First off, we fiddled around with like L1, L2, figuring out how those caches work, came back to it later once we talked about parallelization, but we talked about how to exploit this, basically keeping things on cache lines, which are basically 64 bytes. And then later we talked about, you have to do some, well, with virtual memory, you have to translate it to pages, and we might also have to do some performance optimizations to keep things on certain pages, which we saw with some of the dynamic memory allocation. Then we didn't really talk about disks or anything like that. Not sure why that wasn't included, something else to put in the course. If you do this in practice, you might want to look into things like non-blocking I/O and things like that, so you can actually do some useful work while you're waiting on these slow writes to disk or things like that nature, especially if you have a distributed file system or something like that that could be quite slow. And why caches work is, well, our programs tend to reuse the same memory over and over again, or something close, or something next to it. So two major types of locality. We have temporal locality, so we'll just reuse the same memory locations over and over again. It's very likely whenever we write programs. And then spatial locality, we'll probably access the next element, and, well, our caches and prefetching try to take advantage of this, which we can, of course, help the compiler out if we somehow know our memory accesses better than the compiler. The only example where that actually worked was that binary search example, where it looks to the hardware that you're accessing memory almost randomly, and the prefetcher doesn't work, but for the most part, if you add your own prefetching, you're probably going to do worse than the actual hardware prefetcher. So you want to write code that has locality. Generally, you will be doing this, but in case you have very, very large data structures, you might need to change how your data structures are in memory, so you can take advantage of both of these. So you want to access things contiguously. Linked lists are generally really, really bad for this. Try to lay them out as much as possible. If you're using keys and values and you're always checking the value with the key, you probably want to store them together as opposed to maybe a separate array of keys and a separate array of values. And then temporal, make sure if you're trying to modify the data, you just do it all at once. You don't keep going back to it. So this might have to do with choosing a good algorithm or doing loop transformations. We saw that tiling example when we had a giant matrix multiply where, well, for going one direction, it was good for the caches. For going the other direction, it was not good for the caches. So we just made sure we reused things that were brought into cache. So then we got into dynamic memory management. Talked about implicit lists, explicit lists. So implicit lists, remember, we were just treating the whole block of memory, putting a size tag on it, and then using the space in the middle for the allocation, putting a tag also at the end so we can traverse it forwards and backwards. And then for the implicit list, to do any allocations, we have to search through all the free and allocated blocks, which might be really slow. For the explicit list, we have the same structure, but we also added a linked list of free pages so that doing an allocation, we don't have to search through already allocated blocks, which is a waste of time. And then we had segregated free lists, which just kept track of different lists of different sizes. So we might also figure out, how we pick a block to use for allocation. If many might fit, there's like the worst fit, best fit, first fit, that kind of thing. Then when we reinsert a free block, we had to merge it with the one beside it, so we coalesce things together. So we actually kept track of the largest free hole in memory. And then we briefly went over how PRK malloc and JE malloc work, trying to take advantage of, multiple processors, trying to keep allocations local to a thread for JE malloc, and for PHK malloc that was trying to use pages effectively, and instead of just assuming the heap is just one giant block of memory and that virtual memory does not exist. All right, then we got into multi-threading, which seemed like a lot of review to me. So we figured out how to share data, across different threads. It's all shared by default. And if we do that, we have to keep track of communication synchronization. We might have data races. Data races, again, this kind of feels like review from 344. 2 concurrent accesses to the same location with at least one being a write, in which case you might get some stale value if you allow a data race to happen. To prevent it, we need things like mutexes that ensure mutual exclusion. Only one thread writes at a time. But if we just have one mutex, our program is going to be slow because we're essentially making it serial with the overhead of a lock, which might introduce contention. And it takes a few CPU cycles to even acquire and release the lock. So if we go to more fine-grained approaches where we try and have multiple locks covering smaller areas, we might lead ourselves to a deadlock. So we should know how to use the pthread library. You might use C++ threads. They're going to use the pthread library. Just a better, possibly a nicer way of doing it. And then, like I said, coarse-grained and fine-grained locks, because we will care about performance. So we might have to parallelize some code that looks like this, where we have some dependencies. So we want to make sure we always write to the value before we read from that value. And if we just try to naively parallelize this, we might be reading old values because, we don't know what other threads are at. So each iteration actually depends on the previous, so we have to do some synchronization between these. So we could use semaphores, barriers, or what have you. So then we got into parallel architectures because we know at least at L1, each cache is private to a core. Typically, L1 and L2 are private to a core, and L3 is shared. So because of this, we have to ensure some consistency between the different cores that are all changing memory. So this is where we got into the difference between coherency and consistency, which is where all of the fun things happen. So anyone remember what coherency is versus consistency? Yeah.
Is coherency finding the view of one single piece of memory, while consistency is the relationship and ordering between multiple different pieces of memory?
Yeah. So coherency is the same memory location, the view of the same memory location across multiple cores. Consistency is the ordering between reads and writes between multiple cores. So coherency, same memory location. Consistency, different memory locations. So for coherency, that same memory location, there was this MESI protocol to actually make sure that the cached value was consistent across multiple caches. Here, we started off with just MSI without this exclusive bit, and that caused invalidation on every single core, no matter what, even if a core was the only one to hold this memory value. So we need to add this exclusive state so that we could actually do a local update without causing invalidation to every single other core. And then we had false sharing. Anyone remember what false sharing was? Yeah.
It's accessing different pieces of memory, but they lie on the same cache line.
Yeah, when two cores access different independent pieces of memory, but they happen to be on the same cache line. So according to this protocol, they're shared, even though that specific value might not be shared. So if we have that, that will cause invalidation all over the place and cause all the cores to go really, really slow. And then we figured out, hey, we probably want to add extra padding or things like that so that, well, we don't get this false sharing problem. We don't destroy our caches or performance through cache invalidation. So some other implications of this parallel architecture: that cache coherency was expensive. It's also more than you thought. If you have false sharing, your performance will tank by probably like 10x or something like that. It will be bad. So atomic operations are also somewhat expensive. So for implementing better locks, we might want to avoid unnecessary coherence updates and things like that. If we get a large server, unfortunately for us, we did not have access to a large server with multiple sockets. But if you happen to get access to one of those, crossing sockets, if you have like 2 CPU sockets, crossing that communication barrier is a large killer, because now we're not even doing these coherence protocols on the same chip to cross different chips. Yeah?
Are there tools that'll help us detect false sharing easily?
Perf would help you because you'd have so many more like cache misses.
Right, okay.
So yeah, perf definitely help you there. It won't explicitly say, hey, you're doing a false sharing or anything like that, but you'll see your cache miss just skyrocket, and you can narrow it down to figure out where that's happening, and then you can probably get a good idea of doing that. So like with most things, knowing is half the battle. Whoops, I just wrote a line across that. All right, so if you cross sockets or things like that, well, it can be slower than running the same program on a single core. If you need to mess with the scheduling, there's affinity. So affinity mass is like the odds of that thread to stay on the same core. So if you have multiple or different communication between threads or something like that, you can make sure that, hey, they're all scheduled to be running on cores that are physically close to each other so you don't have the same problem. And this is becoming more of an issue now. If you have like the big new AMD chips, they have like a chiplet design. Each chiplet within a chiplet, it's really, really fast. Across chiplets, it's much slower. Even on consumer CPUs, I think there's like 2 chiplets at least. So might even be a thing for you nowadays, even with a high-end desktop. So then we got into memory consistency. We already talked about the difference between coherence and consistency, and then sequential consistency, which was making sure that reads and writes appear in some order as if they actually executed on a single CPU core. It was really expensive to implement that. Anyone remember why that was really, really expensive to implement sequential consistency? Yeah. Yeah, you can't reorder anymore. That's one of them. Any other ones? Cache consistency had to do it. Well, in order to make sure it was consistent, we had to stall the CPU too, right? Had to stall, wait for a read to appear on all cores. That's also really slow. And also wouldn't be able to use, like, they have a store buffer on the cores. If you're doing that, well, you have to flush the store buffer, in which case acts as if it's not even there. In terms of performance, so all those processor optimizations violate sequential consistency, especially the store buffer is a big one. Out of order, another big one. So we can use things like memory barriers if we really, really need a set order. So there was read barriers, write barriers, and then full barriers. And a read barrier will make sure all the reads before it happen before any reads after the barrier. So we might need to do that in order to implement synchronization primitives and things like that. If you use pthread lock, don't worry about it. They put barriers in it for you so that it performs as you would expect. But if you are writing something that communicates across different cores, you might have to think about memory ordering, because your compiler also might reorder instructions. So just because you wrote them in some order in your program does not mean your compiler is going to output them in the same order, and also does not mean your CPU is going to execute them in the same order, which is fun. So then we got into better locks. So how locks are implemented, mostly, with atomic instructions. So there's compare and swap, test and set, and what the hell is the other one? Fetch and increment or fetch and add or something like that. So those were all of our synchronization primitives, all of our atomic operations that are supported on the hardware. It's expensive because, well, mostly has to deal with the cache reasons. All of those things are slow, especially if something are spinning on the same memory location. You have to make sure all the caches are consistent and all of that. So started off talking about spin locks because they are the easiest thing to implement and the fastest one, as long as we don't care about the busy wait problem. Then we started with a test and set spin lock, and then went to a test and set spin lock. Anyone remember what the hell a test and set spin lock was and why we did that? Yeah.
Is that like when we did our thing without actually checking what the mutexes, just to see if it somehow would work, and then we checked it with the mutex?
Not quite. So our test and set spin lock, remember, it was like a while loop. So while it tried to test and set, and while it could not set it from false to true, just kept on retrying again over and over to set that value. Yeah.
Was that because normal test and set, every time it tries to test and set, it's attempting to write, and that would cause it to ping pong between different caches of different cores?
Yeah.
If test and set is just reading, so it could exist as shared in both caches?
Yeah, so the difference between it is test and set always invalidates all the caches because it tries to write. The test and set would constantly loop just only reading that value, reading it over and over again until it is 0 or false, and then and only then would it try to do that atomic operation that would invalidate all the caches. So that was trying to keep it in that sharing state as long as possible and only trying to do the write when it knows it might possibly succeed. Won't be guaranteed succeed, but it might have to. Then ticket locks. Anyone remember what the hell a ticket lock was? Yeah, remember someone posted they went to Service Ontario, they got a ticket? Yeah.
Your thread, when it gets a ticket, and you just kind of keep on checking to see if the current number in the mutex is equal to your ticket. You're like, oh my god, it's my turn. So you start executing.
Yeah, so you just have another int basically where you atomically increment that. The original number is your number, and then you get the mutex in that order. So you start spinning on that. The major benefit of ticket locks as opposed to the test and set ones is that they're more fair. You actually get things in the order that you request them in, more or less. I mean, the hardware has to break the ties, but you'll get them in some order. They are a lot more fair than the other types of spin locks. And then we got into queuing locks, like, what was it called? The MCS one. I remember queuing locks? A linked list, something about a linked list. That was basically the one where, yeah, it was a linked list and you took the lock and then you got your own local copy of it and then you only spun on your local copy of it. And if something else added themselves to a list, you would let them spin. And this way, the queuing locks played much better with the caches because you only spun on your local variable. And the only global update you did was to add an element to that linked list, which is not that bad. The whole idea was just spin on your own local variable. Of course, we'd have to make sure we didn't do any false sharing or anything like that. We'd have to make sure it was all on our cache lines. So, just talked about how they were implemented and their things. So then we got into avoiding locks, and that was basically one of the last things we did. So, challenges with locking. I mean, they can be slow even with the lock and unlock. Those take time to run. If we have a lot of contention, things are going to be slow. Instead, we could have some non-blocking synchronization, and how it's implemented is while just using those atomic instructions, try and do a simple update. Most of the time, it's done by just updating things locally and then trying to do an atomic update by pointing to the new value. That's most of the time how these lock-free things are done. But we might get into the ABA problem where on one thread, you might assume that if you read the same value twice, that nothing has changed, right? So if I read an A and then I modify and then I write to it and it's still an A, it hasn't changed. So the state of the world is the exact same as when I left off. But the ABA problem is between your two reads of A, something might have come between that, changed it in such the way that it looks like nothing has changed, but another thread actually changed a whole bunch of things. So we had an example with that too for trying to do this with a stack. So then we saw RCU, so that read, I forget what the C stands for. Read something update, wait, read copy update, there we go. It's either copy or create. So read copy update, that was basically, if we're doing an update, well, if we use like a read-write lock, right? We could have one writer and then no readers. It would block all the other readers. The whole idea of the write copy update was even if we are writing a value, we want to still have everything reading from it. Even if it is an old stale value, as long as it's consistent, we don't really care. And what this does is it will actually do an atomic write to it. Other threads might get an old value, but if you wait long enough, then that writer can go ahead and remove that old value because it's guaranteed that all of the readers are already done with that old stale value. So that's one way we can actually update things so that we might get an old consistent state, but if we don't care about that, this will cause things to be a lot faster, and it's really good massively parallel systems where writes are fairly uncommon. So that's pretty much it. So what we learned, lots of stuff. So sequential program optimization, then parallel programming on a distributed system. So some things we didn't get to / removed because it's in your distributed computing course if you've took that. So we only talked about MapReduce. That was by intention because I don't think the other section probably won't get to that anyways. So I'm not going to talk about it. So we did get to MapReduce. Why do we need MapReduce and what is it? So for the most part, it's a programming model for big data analytics where the programmer has the simple task of just writing two functions, a map and a reduce, and then the system takes care of the rest, takes care of all the nitty-gritty details, which is mostly what system programmers have to do, balancing all of the processing across multiple machines, making sure that in the event of a failure, things can still progress and recover, and you as a programmer do not have to worry about it. But a lot of this is more like in a distributed computing course. So technology is always changing, always have better tools. So Moore's law on a single core, I mean, we're just getting more and more cores. Again, heat laws or whatever, we can't push frequency of cores much harder than we can now. And then we have to rely on parallelism. Mostly we focused with parallelism on a single machine, but of course you can have parallelism across multiple machines in a distributed setting. But our focus was mostly just running on a single system. So what have we learned that's still going to be useful? Well, it's going to change. So some techniques might not be relevant. Some things may change. The answer I always like giving, that was always true, was it depends. So this is what it is like now. The whole purpose of this course is to know that, hey, you should probably know what you're programming for and some hardware details, which is a good thing you are in ECE. And you actually know how some of this stuff works. We have to make sure that things are correct, easy to program, scalability, energy consumption becoming more of a thing now as well. Better programming tools. I'll start to introduce Rust on Friday, which is a newer language that you will probably not be tasked with writing immediately, but it will help you because it, unlike C and C++, is actually built to deal with helping you program with multiple threads and making sure your program is correct, which C++, with all of its warts, absolutely does not do. Even the newest standards with move semantics and all that. We'll show examples on Friday and stuff. Basically, if you are doing any serious systems programming, you should seriously consider starting writing in Rust. Again, we'll see it, but the key ideas will still hold. There's really nothing new. There's always going to have to optimize for the bottleneck. We'll always have caches. There'll be CPU caches, memory caches. As you go on, you might discover caches at different levels, like memcache, so that's like a web cache, basically just caches API calls. CDNs, caches web content. Again, this is more for web stuff. Parallelization will always be a thing because, well, we can't just make things go faster on a single core. And the other thing I like saying is the quickest thing to do is to do nothing. So that will always be true, no matter what. So remember those two things. Fastest thing to do is nothing, and then it depends, and then you're good. So the more important part is to think about the why and not the how. For each technique, we tried to focus more on the why does this happen. So why does cache coherency impact performance? How is just a natural consequence of understanding why. You should always be able to answer the question why if something bad happens. Otherwise, you will probably fall into the exact same mistake. Again, always have some skepticism and some curiosity. Do we really need this thing? Is it helping me? What is actually going on under the hood? So that is the end of the content for at least on the exam. So you survived for the most part. You still have to do lab 5, I guess, but we're almost done. So congratulations, you survived. Hopefully you found it worthwhile. Good luck on the exam. Again, we'll have more fun times on Friday and Monday. We can do a little bit of rest. But as far as the course content is concerned, we are free. Joy. So if you haven't done it yet, please submit your course evaluations. The big crux of this was introducing that compeng.gg stuff and making that a lot easier, and hopefully that was good to submit your assignments to, as opposed to some servers that may or may not crash. So if you, and again, this is the first time me doing this course, and I had to coordinate with another section, so I couldn't just randomly change things. I hopefully want to do that in the future. Well, I will do that in the future. So please fill that out. Those evaluation forms keep me employed. So if you would like me to still remain here and have a job, please fill them out with hopefully nice things, or at least things, constructive things. But yeah, I didn't want to change too much this semester again because 2 sections, first time teaching it. I didn't want to rock the boat too much. So I already have some ideas, but I'm glad to hear more. So with that, we can wrap up. Again, I'll be here the next 2 lectures, but not learning anything. Well, we'll learn something new, but nothing testable. So just